Hey guys, we are continuing chapter 10. We have made it to section 5, where we will discuss probability using permutations and combinations. So in section 10.4, we use tree diagrams and tables to find sample spaces and the number of outcomes in certain events. This was a pretty good strategy, but when the number of possibilities get larger, diagrams can get out of hand. Fortunately, we know about counting techniques that are tailor-made for answering questions about probability. If our job is to find how many ways something can happen, the combination and permutation rules from 10.2 will be our best friends. So we will have to dust off our brains from a couple chapters ago, or not couple chapters, a couple of sections ago, to remember those combination and permutation rules. Okay, and then we are going to tie that in with probability. So our main tool will still be the formula for theoretical probability, which is dividing the number of outcomes that satisfy a certain event by the total number of outcomes in a sample space. But now we'll be able to answer some tougher questions using counting techniques to count outcomes. So let's go ahead and jump into our first example. It says using counting techniques to compute probability. Stacy has the option of selecting 3 books to read for a humanities course. The suggested book list consists of 10 biographies and 5 current events books. She decides to pick 3 books at random. Find the probability that all 3 books will be biographies. Okay, the first thing we have to ask ourselves is does the order matter? No, the order does not matter. So this will be a combination. So we know we'll have to use P. Yep, just said combination and I wrote permutation. Combination N and R on that side. Okay, so the main question here is how many ways can we choose 3 books from 10 biographies? How many ways can we choose 3 books from 10 biographies? So we're going to have to find the combination of our biographies, which would be 3 from that 10, and we'll also have to find the combination of the total books, which would be out of 15 books total. That's the 10 plus the 5, but we still want just those 3 books. Okay? So remember our combination formula is n factorial over n minus r factorial times r factorial. So 10 factorial, 10 minus 3 is 7 factorial, 3 factorial. Write that out. 10 times 9 times 8 times 7 factorial over 7 factorial, 3 times 2 times 1. The 7's cancel out. 10 times 9 times 8 gives me 720. 3 times 2 times 1 gives me 6, which means I get 120 ways to pick 3 biographies from 10 bios. Now I need to figure out my total. So this would be 10 factorial. Oh, not 10 factorial, 15 factorial. 15 factorial, and then 15 minus 3, which is 12 factorial, 3 factorial, 15, 14, 13, 12 factorial, 12 factorial to cancel those out, 3, 2, 1. So I have 15 times 14 times 13 divided by 6. Let's get my calculator to recalculate that. 15, 14, 13, 27, 30 divided by 6 equals 455. So that's 455 total choices when picking a biography. When picking 3 books. So our probability will be favorable outcomes out of total outcomes. We can divide that and we get about 0.264. Remember, this is my total, and this is what I'm looking for. So that will be my probability. So now we're tying in the techniques that we have already learned, understanding the difference between a combination and a permutation, and understanding how probability works, favorable outcomes out of total outcomes. So Let's go ahead and move on to our next example. Yep, super. There are 12 women and 5 men in the seminar course. If the professor chooses four-person groups at random, what is the probability that the first group chosen will consist of all women? Okay. All right. Well, let's work it out. The first thing we need to look at is that we have combination. We're not looking for order, but we have a total, so 12 women, total of 12, and we're picking 4 people. And then we also have, remember this is the 12 from the women. And then we also have the 17, because that's the 12 plus 5 for our total. And we're still picking 4 people. So to write this first one out, we need to take 12 factorial, and then 12 minus 4, which is 8 factorial, 4 factorial. End at that 8 factorial, cancel those. All right. 495 possible ways to have all women. And then we have 17 factorial. And then 17 minus 4 is 13 factorial, 4 factorial. That's not supposed to be dot under there. 13, 13. Do the math, 2380. Okay, now the last step is to find that probability. The last step is to find that probability. So all we have to do now is divide the 495, 2380. And we get about 0.208. That's our probability. All right, let's look at another example. This example says, what is the probability of getting 4 aces? Oh, I'm sorry, guys. What is the probability of getting 4 aces when drawing 5 cards from a standard deck of 52 cards? Okay. All right. First, we'll figure out how many 5-card hands have 4 aces. How many 5-card hands have 4 aces? The key observation is that we need to get all 4 aces in the deck. There's only one way we can do that. So after we have our 4 aces, we still have to choose a 5th card. That means that there are 48 other cards left in the deck. Using the fundamental counting principle, there are 1 times 48 possible hands that have 4 aces. In other words, if you get all 4 aces in the deck, that's your 52 in a hand, that's your 52 minus 4, which is going to give you your 48, which means you have 48 other options left that you can match up with each of those aces to have a 5-card hand with 4 aces. Okay, does that make sense? You have 48 other cards left that you can create this 5-card hand and include those 4 aces. All right, so we have, like I said, 48 possible hands that have 4 aces. Order doesn't matter again, so the total number of 5-card hands is a combination problem where we will have 52 as our total, and we want 5 at a time. Okay, we want 5 at a time. So this is how we're going to find our total, our denominator. This is how we found our numerator. Okay, our top number, because we're looking for getting 4 aces when drawing 5 cards. So there are 48 different hands we can do that with. And then this bottom part, 52 factorial, and then 52 minus 5, which is 47 factorial, and then 5 factorial. So I'm going to go ahead and start writing this out. 50, 49, 48, 47 factorial. These are huge numbers. 5, 4, 3, 2, 1. So we have 2,598,960 as our denominator. So our probability will be 48 out of that 2,598,960, which comes out to about, look how tiny this number is, 0.0000185 as our probability. All right, let's look at another example. A combination lock has 40 numbers on it from 0 to 39, 0 included, which means it's 40 numbers because it only goes up to 39. Find the probability that if the combination to unlock it consists of 3 numbers, it will contain the numbers 1, 2, and 3. So if it consists of 3 numbers, we're looking at just the numbers 1, 2, and 3 in some order. Assume that numbers cannot be repeated in the combination. And this is actually something I mentioned in the last video. It's interesting to note that a combination lock should really be called a permutation lock, since the order of the numbers is important when you are unlocking the lock. All right. What we need to look at here is that order matters. And that order matters because it tells us that in the problem. It contains 3 numbers in some order. Just trying to find it. I'm like, I know it's in there. All right. So it told us that the order matters when opening the combination lock. So we're dealing with a permutation in this problem because order matters. So now we're looking at our permutation formula. And just a reminder, permutation was n factorial, n minus r factorial. Okay. So the number of combinations for the lock containing 1, 2, and 3, we are looking at 3 and 3. Plug those numbers in, and that's because that's 1, 2, 3, and we want 3 numbers, okay? And those numbers are 1, 2, and 3. So we have 3 factorial, 3 minus 3, which is 0 factorial, which we already discussed this one. So that's 3 times 2 times 1 over 1, which is just 6. So the total, the number of combinations for the lock containing 1, 2, and 3 will be 6. Now we have to look for the total number of combinations as a permutation of the 40 numbers taken 3 at a time. So now we're looking at it with 40 taken 3 at a time. 40 factorial, 40 minus 3, which is 37 factorial, which is 40, 39, 38, 37 factorial, 37 factorial. Cancel those out, and we're left with 59,280 as our total. And let's see, making sure we're answering what the question was asking us. Find the probability. Yep. All right, so the probability of the combination containing 1, 2, and 3 would be that 6 out of 59280, which is about 0.000101. Couple of steps, but once again, they're the same steps. First, you need to look at if order matters or does not matter. That's going to help you decide if you have to use the permutation formula or the combination formula. Once you figure that part out, you're looking for those specific numbers and your total. Your total is going to be your denominator. And you come over here, you turn it into a probability, you divide, and you come up with your final answer. All right, let's look at another example. Our last example, actually. A store has 6 different fitness magazines and 3 different news magazines. If a customer buys 3 magazines at random, find the probability that he'll pick 2 fitness magazines and 1 news magazine. Okay? So let's look at the information we have. We have 6 different fitness magazines and 3 different news magazines. He's looking to buy 3 magazines at random, and we are looking to see what's the probability that he'll pick 2 fitness magazines and 1 news magazine. Okay, so does order matter? No, doesn't matter which order he picks them in. So we know we're looking at a combination. All right, so we want to know how many of each magazine the customer buys. Not the order. We don't care about the order, which is how we came up with the idea that we're using a combination. So we have 6, 2 here to figure out the 2 fitness magazines and 6 fitness magazines. And just in case you're wondering where those numbers came from, we have 6 different fitness magazines, and we're trying to choose those 2. So our 6 goes here as the number, and our 2 is how many we're choosing. So 6 factorial over 4 factorial, 2 factorial, 6, 5, 4, 4, 2, 1. 30 divided by 2, which equals 15. Now I need to do the same thing for the news magazines, but with the news magazines, I have 3 that I can choose from, and I want 1, so that's 3 and 1, so that's 3 factorial, 3 minus 1, which is 2 factorial, 1 factorial, 3, 2 factorial, 2 factorial, 1, cancel, cancel, equals 3. Okay, give you a second to look at that. Okay, all right, we're not done yet. We now have the word and in this event. So we can think of this as a 2-step process and use the fundamental counting principle to multiply, giving us 15 times 3, which is 45 ways to pick 2 fitness and 1 magazine and 1 news magazine. So we're going to take that 15 times 3 using the fundamental counting principle to come up with 45 because we're using that word and. Now we need to figure out the total from all 9 magazines. So this is where we have to do one more. 9, and we're still just picking 3. We're still looking for 2 fitness and 1 news out of the total of 9, that's 6 and 3, okay? So first we start off separate. We start off looking at just the fitness, just the news, and now this is together, okay? Before, we only needed one of those and then our total, but because we're using the word and, we're putting 2 of them together. That's why we are using the fundamental counting principle with that 15 and 3 to come up with this 45 as our numerator. Okay, now I have to do my combination formula to find my denominator, which is going to be 9 factorial, 9 minus 3 factorial, 3 factorial, 9, 8, 7, 6 factorial, 6 factorial, 3, 2, 1. Those cancel out. I end up with 9 times 8 times 7 divided by 6, 84. So that's my denominator. My numerator is 45 out of 84. I can divide that and I get about 0.536. Okay, so we're building on the concepts that we've already came up with. As you can see here, we included combination, we included the fundamental counting principle, and we included probability. The same thing with most of these. I did, however, want to go back to example 4 very quickly. Here it was saying in some order, what if, so let me say this, okay. Here, I just wanted to throw this in. The numbers are not being repeated. Okay, that's why we're taking one away each time, right? 40, 39, 38, 37. What if the numbers could be repeated? What would we do if the numbers could be repeated? If they could be repeated, this would be 40 times 40 because that's how many numbers we have. That means that each time we have 40 options. Each time we have 40 options. So in this case, we can take that 40 times 40 times 40, and we've seen this in the other section also, to come up with 64,000. So if we were asked the probability, then we would make this our denominator, and we can say 6 out of 64,000, and that gave us about 0.0000937 Okay, I just wanted to point that out that the reason when we're using the factorials is because something is not being repeated, it's consistently being taken away each time. Whereas if we could use the same number or letter or whatever it is we're looking for, that number would stay the same and it wouldn't be considered a factorial. So just wanted to talk about that. Now, don't get that confused. You still have to use this formula with the factorials for this problem. This is just a separate way of looking at the same problem, but saying that those numbers can be repeated. Okay? All right. That concludes section 10.5. Those are your discussion questions that you can read over. And make sure that you are emailing me